All right, let's look now at section 14.8 and talk about Jacobians. We've seen change of variables lots of times. Going back to Cal 1, if you have an integral from a to b of f of x dx, you can always change variables into a different kind of variable. Here, you can take x, and instead of having x be just x, you can consider it as a function of another variable. Usually we use the u substitution, but you can use any letter you like. So here we could say something like let x equal to g of u. So x isn't really a variable, it's a function of another variable. Right? Composition. Right? So here we would say, okay, well, if that's x, well, then we have to change our differential too. So we would say, okay, so now dx is equal to g prime of u, and then the differential of the original variable here is du, something like that. So here you could rewrite this as the integral of, instead of f of x, you could write it as f of this function. So f of g of u. But now notice that when you change this differential into the differential with respect to this new variable, it's no longer just dx and it's no longer just du. You have this extra bit of something, namely g prime of u du. All right? The chain rule. And of course, here we could change our boundaries as well, because after all, if here we're saying x is equal to a, well, then you say, all right, well, if x is equal to a, then that means that g of u is equal to a. Okay, so that means there must be some new variable, u, that if I plug into g, gives me a. So here we would say, okay, well then that would be u is equal to g inverse of a, which is just a number, right? You're taking a number and plugging it into a function. So here we've already used a and b. We can call this, for example, c. Okay, so that's our lower bound. And if you have your upper bound, if f of x is equal to b, well, that implies, well, that's b is equal to g of u, which means that u is equal to g inverse of b, which means, well, you've just taken the number b, that was just a number, and you plugged it into some function, which gave you some other number. So here we'll call this one d. And that's what change of variables looks like. You change not only your variables, but also your boundaries and your differential. This is the part we want to focus on right now, because notice that when you're changing variables, there's this extra little bit of something that also comes along from the chain rule. Well, note that for one variable, it's always the same thing. It's just, okay, whatever you called your u, then you're going to want the derivative of that du. For higher dimensions, for when we're looking at iterated integration, we're going to end up with something similar that's called the Jacobian. So let's begin with our definition. So let's define two variables, x and y, not as their own separate entities, but as functions of some other set of variables. So here, let x be defined as a function of two other variables. And here we're going to, in keeping with what notation we use for a single variable, we're going to say g of u, but we're going to need a second variable. So here we're going to say uv. So let x be given as a function of two variables u and v, and let y be given by some other function, also of u and v. Right? Then the Jacobian of x and y with respect to these two variables is given by, so first of all, the notation, that's del x comma y over del u comma v. This is just a notation. This doesn't tell you anything about how to compute it. This is just, if you see this, the way this is read is Jacobian of xy with respect to uv. All right? So now, how do you compute that? That's given as follows. It is the determinant of a matrix. And that matrix is made up of all of the different partials that you can get of x with respect to u or v and y with respect to u and v. So here that's going to be partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, and partial of y with respect to v. Remember how determinants of a 2 by 2 matrix work? We're going to go ahead and take this product minus this product. So here, this is one way to remember it as the determinant of a matrix, but you could also write it in its longer form, namely, it's the partial of x with respect to u times the partial of y with respect to v minus the partial of x with respect to v times the partial of y with respect to u. Right? So you can either remember it as a determinant or just remember this. That being said, remembering it as a determinant is convenient because you won't always just have two variables. You can also have things like x, y, and z, for example, like we have in spherical and cylindrical coordinates. Or you could have 4 or 5 or 6. And as such, a determinant is usually more convenient to remember. Right? So here it's just this one and then this one. First and second, yeah? And this brings us to our theorem for the section. And this is how we change variables. So here we're going to be looking at double integration. We're not going to worry about triple integration for most of this section. At the very end, we'll give one quick example about triple integration. But for the most part, it works the same for any number of dimensions, x and y, or x, y, and z, or whatever. It's just, in this section, we pretty much restrict ourselves to functions of two variables. In any event, here we're going to talk about our change of variables theorem. And we're going to start off with a function that is, a region. Let's call it R. So let R be a region in the xy plane that is either, it doesn't have to be both, it could be either vertically or horizontally simple. Remember what that means. It just means if it's vertically simple, that means the top and the bottom are flat. If it's horizontally simple, it means the left and the right are flat. All right? And that's all we're saying. We have at least one side which is nice and flat. We're going to go ahead and pick another region in a new set of coordinates. Let S be a region in the UV plane. Now here we're talking an abstract U and V. However, we've seen examples where these are not abstract. We have, for the most common example we've seen has been the R theta plane, right, in polar coordinates. But here, this could be anything. And as we'll see in this section, it will be anything. So let S be a region in the UV plane that has the same conditions. That is either vertically or horizontally simple. Okay. So now let's take a function. Let T be a function such that T maps something from R into S. Let's go from this one. From S to R. So in other words, a function T just takes you from this coordinate system into this coordinate system. Is defined as defined by T of U comma V. But since, again, U and V, we're going to consider these functions of variables in our other plane. Here that's going to be X comma Y, which is really given by G of UV comma H of UV. Or in other words, you start with a point in the UV plane, You apply the function, and it gives you a point in the other plane, in the xy plane. And the way you got that point is by taking the original u and v and applying some function g to it. It's a function of two variables, and that gets you your x. Applying another function h to those same two variables gives you y. All right? So t is really composed of two variable functions, one which turns uv into x, one which turns uv into y. Okay? So we have our function t. Now this is leading toward use of this, so we are going to need to have at least one derivative. We're going to need to know that this partial exists. So here we want g and h have a continuous first partial derivative. So these are just regular functions. So here we're just going to say I have continuous first derivatives. We just want to know that these exist. Okay, now we need to have, so let t be a one-to-one function. We need to be able to go back and forth. Let t be one-to-one, except possibly, we can make an exception, on the boundary of S. So it has to be one-to-one in the interior of S, but if you're on the boundary of S, it's okay if you have some points which are not one-to-one, except possibly on the boundary of S. So these are all of our conditions. So this brings us to our conclusion. The double integral over the region R, which was the place where our function mapped to, it's the one on the xy plane, the double integral over the region R of f of x comma y dA can be given by the double integral over the region S of f of u, well, it is a function of u and v, but I suppose I should label it with this notation. So f of g of u comma v comma h of u comma v times the Jacobian partial xy over partial uv. We're going to take its absolute value with respect to u and then with respect to v. All right. So this shows us that we can change from, provided these conditions are true, we can change this double integral in R to this double integral in S, provided that we change our variables, but also multiplied by this extra term, or by this extra factor, I should say, which is the Jacobian, the absolute value thereof. This is true provided that your Jacobian's absolute value is not equal to 0, provided that the Jacobian of xy with respect to uv is not equal to 0 on S. Because if it is, well, then you have 0 and, well, everything goes away. And also provided that on S, and that here we need this to be continuous as well. The function f, the one that we're integrating, f is continuous as well. Okay. The proof of this is just like most of the proofs that we've seen throughout this course, we're going to approximate something and then make the approximation good. All right, so proof of this, let's begin with a, well, let's see. We have R is a simple region in the xy plane, and we have S as a simple region in the UV plane. So here, let's start with, and since we know T is going to take things starting from S into R, well, then that's going to be, let's start with S. Okay, so here, visually, let's assume that you have a very simple region in the a very simple region S in the UV plane. So here's the UV plane, like the R theta plane or whatever. Here we're being generic about it. Now, whatever this shape is can be broken up into little rectangles. So without loss of generality, we can look at just one of those little rectangles. If whatever we prove is true for one little rectangle, then it would be true for everything. Because after all, that object is made up of just little rectangles. So here, let's consider a little tiny rectangle in the UV plane. Okay. Once again, this is just one little tiny piece of something bigger, but if we can prove it for this one, well, then it must be true for all of the little pieces, all the little patches, which means that it must be true for the entire region. Okay, so here we're going to take a point, and we're going to take a point xy, although since we're in the UV plane, it should be u comma v. All right. Now, here are four other points, or rather three other points, and they're very, very close to this point. Remember, we said this is a tiny little square, a little rectangle. We've blown it up, we've zoomed in, but it is supposed to be very, very tiny. So the distance from here to here is just a little tiny perturbation, a little tiny change in the direction of u. So let's use the notation that we're familiar with. We're going to add a little bit of extra u to that, right? Comma v. All right, so that's that point. And same thing over here, that's a little something extra in the direction of v. Okay, so that's going to be u comma v plus delta v. And then this one is, it's got the same u value as this one. It's got the same v value as this one. So this must be u plus delta u, comma v plus delta v. Okay, so now this is a function in, this is a region in the UV plane. You haven't defined a function yet. Okay, so since that's a function in the UV plane, we're calling that one S. So we'll say, well, that is S. So now we have a function, which we're calling t, which will take this into the xy plane. Okay, so here's the traditional xy plane that we're used to ever since we were in grade school, the traditional xy plane. Okay, so now this transforms into this. You say, well, that could be anything. Well, not really, because after all, this is supposed to be continuous, right? We said let t be a continuous function. All right? Where were we here? So let t be a function that is defined by this, where g and h have to be continuous. Okay, so because of the continuity, that means that if I take a little tiny change here, that's got to convert into a little tiny change over here. Now, it doesn't have to be in the same direction, but it does have to be a continuous function. All right? So here, remember, this is made up of continuous functions. This is t of uv. And recall that we have the f and g are continuous. All right. And remember, the loose definition of continuity is if you have a little tiny change in the domain, that leads you to nothing more than a little tiny change in the range. That's not the formal definition, but it's a nice loose definition that we're going to apply here. Okay, so if this is a little tiny line segment, over here, the worst that could happen is you end up with a little tiny squiggle. That's the worst that can happen because the thing that transformed this is made up of continuous functions. All right. The thing that transformed this first variable is this function, and the thing that transformed this second variable is this second continuous function. And likewise for all of these. Here, these 4 points are going to change to something that is not terribly far away from being a parallelogram. Okay? Now, this may or may not be a parallelogram, but it's not terribly far away from being one. So here we're going to say, okay, so let's approximate this. Here is my region R, but I don't want to treat that as R. What I want to say is, well, here, let me call this R. And what I want to say is R is approximately a parallelogram, more or less. So here, let's go ahead and label these corner points. And we'll use the M, N, Q, and P, like this. All right. So now notice that even though this may or may not necessarily be straight lines, we can approximate them with straight lines. Here, the area of the region R and the area of the parallelogram that I've just drawn are approximately the same. So here we're going to say, okay, the area of here, the area of this little region, is given approximately by the area of the parallelogram. So the region R has area approximated by the parallelogram, MNQP. Okay. All right, well, we remember that if you're trying to find the area of a parallelogram, one way to do that is with the magnitude of the cross products. So here, the area of the parallelogram, I don't know how to spell parallelogram, there we go, is given by the cross product, or the magnitude of the cross product, of adjacent vectors. So here we could say, oh, well, let's do the vector from M to N, and let's do the vector from M to Q. All right? So here that's MN crossed with, let's say, MQ. It didn't have to be those. We could have said PN and PQ or QM, QP. It doesn't really matter. But here we're taking two adjacent sides, taking their cross product and the magnitudes. And this goes back to chapter 11. We saw this when we first introduced cross products, 11.3, I believe. Oh, so then that means that the area of the region R is approximately given by this. So here, so now we ask, okay, what is this vector? And what is this vector? What is MN? What is MQ? Well, MN is approximately what happened when I took this little line and turned it and passed it through this function to give me something in the xy plane. And remember how that works. If we're passing something through the function t, that means we're passing the first component through f and we're passing the second component through g. All right, if you plug u and, oh sorry, I said that wrong. We're passing both components through f to give us the x value. We're passing both components through g to give us the y value. Yeah, I said that wrong the first time. So here we have, well, these two must go through f to give me that point. Those through must pass through g to give me the y component of that point. Separately, these two must pass through f to give me the x component of this, and these two must pass through g to give me the y component of this. Oh, okay. So then that means that Mn is going to be given by, well, let's see here. Whenever we have a vector, we give the terminal point minus the initial point. Okay, so that's going to be the vector given by n minus m, all right, which is going to be given by, well, let's see, n is what you got when you took both of those and passed them through f and g. Okay, so that's going to be f of u plus delta u comma v, and that's the first component, and then g of u plus delta u comma v, like that. And then we're going to subtract away. Okay, well, m came from this point, so we're going to take both of those and pass them through f, and then take both of those and pass them through g, and that'll give us our, oh, did I mess up the name of my functions? I did. My apologies. Over here, t, it wasn't f and g, it was g and h. So that won't cause a major change here, but this is g and this is h. So here, this is, let me write that a little more cleanly, g and h. So here, that's only going to cause a change right here on us. We're taking this and passing it through g to give us our x value, and we're passing it through h to give us our y value. And again, that's a point. And we're going to make a vector by subtracting away the components of these points. Okay, so that's going to be, now we're doing uv through those. So that's going to be g of uv, comma, h of uv. All right, that's the point. If we pass it through g, that gives us the first component of that point. If we pass that same point through h, it gives us a second component of that point, like that. And so this is going to give us the vector, and now we subtract the two components. That's going to be g of u plus delta u comma v minus g of u comma v, comma, and then here we're subtracting those corresponding components. That's h of u plus delta u comma v minus h of u comma v, like that. But notice those look familiar. Those look like the numerators of a partial derivative. If this was just over delta u, that would be the partial of g with respect to u. Same thing here. If this was over delta u, then this whole thing would be just the partial with respect to u. Or at least it would be when we pass through a limit, which of course we know we're bound to do that at some point. Oh, okay, well then all that means is that this is the partial times that denominator. You say it is? Well, approximately. Again, we haven't passed through a limit, but keep in mind that these are very small numbers that are very close together. So even though this is not exactly the partial times the denominator, it's approximately equal to that. So this is approximately equal to, this is, let's see here, that's going to be delta, or yeah, del G, del U. Oh, here, let's write it as G sub U, because otherwise my notation is going to get big. So that's going to be the partial with respect to U times what should have been the denominator. And that's not exactly true, but since these numbers are all very close together, right, since delta U and delta V are very, very small, it's approximately equal to that. Likewise, this is the numerator of H sub U, or at least it almost is. So here we can write this as it being approximately equal to H sub U delta U, like that. Okay? And again, this is okay because delta U is very, very small. And you can do the same thing for this other vector. You can say MQ is going to work the same way. MQ is simply given by the Q minus M. And I take the destination point minus your original point, which is going to be given by, and here Q came from this point, which you notice here the U stayed exactly the same. It's the V that's changing. So here that's going to be G of U comma V plus delta V, comma H of U comma V plus delta V, minus, and then over here we're going to take the initial point, which we saw already was G and H of U and V respectively, because it's the same M. So that's going to be G of U comma V comma H of U comma V. And then to create our vector, we're going to subtract corresponding points, corresponding elements of our points, which will give us G of U comma V plus delta V minus G of UV, comma H of U comma V plus delta V minus H of UV, just like that. But of course here, just like over here, these are the numerators of a partial derivative. But notice here, instead of changing the U a little bit, you're changing the V a little bit. Okay, so that must be a partial with respect to V instead of U. So approximately given by G sub V delta delta V, comma, and same thing over here. This would be the partial with respect to V of H if only it had the denominator of delta V. Oh, well, we can multiply that off to the other side, and that'll give us H sub V delta V. And again, none of these are exactly equal. This is not exactly equal to that. This is not exactly equal to that. This would be equal to this one if we took a limit. Same thing here. But since delta V is very, very small, even without taking a limit, this is already pretty close to being true. So this is because delta V is very small. So now we can take the cross products of both of those. We want mn cross mq. So let's see what that looks like. Let's take mn cross mq, like that, which is what we want. We haven't taken the magnitude yet. We're taking the cross product first. And that's given by, well, we had a nice shortcut for taking cross products. We took this, and then we wrote down the components. And notice the components of mn are given by, well, this one. Oh, you know, our third component isn't there. There is no third component here, right? This is just in 2 dimensions. Okay, so here we can write this as the partial of, oh, let's see, which one am I looking at? The partial of g with respect to u. That's mn, yeah. So that's the partial of g with respect to u times delta u. The next one is going to be the partial of h with respect to u. So del h del u delta u. And then here we don't have a third component, so here we're going to fill this in as being 0. So let's see here. Let's come up here and just fill these all in as being 0. We want all of these to have 3 components so we can take a cross product. If it doesn't have a third component, then the cross product is not defined, and that would not be good for us. All right, so here that's going to be just like that, just a third component of 0. Doesn't change any of our previous computations. It just allows us to take a cross product here. Okay, so now this is del G del V delta U. Oh, sorry, that should be delta V. I'm just taking these components here. And then this one's going to be del H del V delta V. And then 0. But remember, G is a function that transforms UV into X. And here, this H transforms UV into Y. So when we say partial of G and partial of H, we can just be saying partial of X and partial of Y. So here this would be I, J, K. This would be the partial of X with respect to U, delta U. This would be the partial of Y with respect to U, delta U. Notice this is starting to look like the Jacobian here. This is the partial of x with respect to v delta v. And this is the partial of y with respect to v delta v. And of course, these components are 0. Okay. But now, if we go ahead and take the determinant of this, we could use the minor's method. And we could say, okay, let's take the minor of k. You may not remember the minor's method. Basically, the way it works is you pick one element in your matrix, like this. It doesn't matter which one you pick. You can ignore all of the elements that are in the same row and column, and the determinant of this matrix is simply going to be given by this times the determinant of what's left. And then you would repeat that for this element and for this element. You pick all the same elements in one row. But notice, since this one's 0 and since this one's 0, 0 times any other determinants will be 0. All right, so once again, I'll take this one, ignore all of these, and say, okay, I'm going to take the determinant of what's left times that element. All right, and that's a 2 by 2, so that's just going across. Oh, but then I would take this element right here, and I would do the same thing. I would ignore everything above and below. And everything to the left and right, and take the determinant of what's left. The determinant of I times that minus j times that. But again, since that one is 0, the whole thing would equal to 0. And same thing for this one. So in the end, you're only going to be left with this one times the determinant of this. Okay, so that's going to be, well, let's see, that's going to be del x del u delta u times del y del v delta v minus, and then we're going this way, del y del u, delta u, times del x del v delta v. And all of this is just the third component. The first component and the second component will be 0 because the minors of those will be 0. If that minors method is a little foreign to you, it's a little something that's not familiar to you, you may wish to just use the longer method of using the crosses, subtracting out. Either way, you'll get this result. Notice here I have a common factor of delta u delta v, delta u delta v. So here this can be written as del x del u times del y del v minus del y del u times del x del v times delta u delta v, which I've gone ahead and factored out, k. Or more simply, if you look back at our definition from before, this is the Jacobian. So here you can write this as the, let's see here. That's going to be del x. Let's see. I already forgot my notation. It's del x comma y over del u comma v. That's why I keep this page right next to me. I already forgot my notation. I'm used to writing the Jacobian just as a matrix. I'm not really used to using this notation here. So here that's the Jacobian times delta u delta v times k, which really means this is the third component. If you wrote this in this form, it would just be 0 plus 0 comma 0 comma this thing right here. And so we're just about done. Remember that what we were trying to do was we were trying to approximate this area by taking the magnitude of this cross product. Okay, well, we found the cross product. So now let's go ahead and find its magnitude. So the cross product of mn with mq is given by, and here I'm going to write this in the other form, in the vector component form. I'm going to write this as 0 comma 0 comma the Jacobian of xy with respect to uv times delta u delta v. Right? That's what this k is telling us over here. That's telling us, that's only the third component. But our first and second component weren't there. So they must be zeros. Okay, then that means that if I want to take the magnitude of those, well, then that's going to be take each of those components, square them, add them together, and then stick them under a square root. Okay, well, here 0, 0, those are all 0. Here I'm taking the square of something. These are already positive. We don't know what this is. Okay, so if I square it, it may either remain exactly the same or change its sign. But then when I take a square root, the square goes away, and I'm just left with the original expression minus any negative it might have had. That's just called the absolute value of something, isn't it? So here that's going to be the absolute value of this, the absolute value of the Jacobian times delta u delta v, like this, right? Here, those contribute nothing. Here, these were already positive, so taking their square and square root changes nothing about them. But this, well, we don't know what it was. So taking its square and its square root gives you the absolute value by definition. So that means that the small little change of area in the xy plane, that means this little area here, and remember, it is a little tiny area. That was the initial assumption, assuming we have very tiny little patches of things. Then that means that the area, and here I'm going to put in quotes, tiny, the tiny area in the xy plane is delta A, because after all, that's the notation we usually use for a small little bit of area. Delta A is given by, is approximately given by the absolute value of the Jacobian times delta U delta V So now let's take the limit of both sides. Let's take the limit as the norm of this partition approaches 0. And that's approximately equal to the limit as the norm of this partition approaches 0 of the absolute value of the Jacobian, delta U, delta V. But of course, these are differentials. So here we end up with dA is approximately given by the absolute value of the Jacobian times dx dy. And so if we're changing our variables, this differential in terms of area, can be written as the absolute value of the Jacobian times the differential of your new variables, just like that. Oh, and I've written the wrong variables here. Del U, del V, that should be du, dv. Here, let's just rewrite that. Du, dv. And there we go. So our differential in terms of area can be given by the absolute value of the Jacobian times the differentials in your new coordinate system, which is what we were looking for to complete our proof. This becomes this. So that means that the double integral over the region R of f of x comma y dA can be written as the double integral over the region S, with x being substituted as g of uv, and with y substituted as h of uv, times the absolute value of the Jacobian, du dv. All right, now, as an example of this, let's start off with a really, really short one that's familiar. Let's talk about the following. Let's compute the Jacobian of the transformation where x is given by r cosine of theta and y is equal to r sine of theta. Polar coordinates. Okay, well, let's see here. The Jacobian is given by, it's a determinant. We're going to take the partial of x with respect to one of the original variables here. So partial of x with respect to r. And then we're going to take the partial of x with respect to the other variable. So that'll be del x del theta. And now we're going to go back and we're going to use y. So it's going to be del y del r and del y del theta, like that. And now we're going to take a determinant. Okay, well, let's actually see what those are. The derivative of x with respect to r, well, that would make r a variable. So this would be a constant times r, and the derivative is just that constant. Okay, so that's cosine of theta. The partial of x with respect to theta, okay, now that's a variable, and that's just a constant. So the derivative of constant times cosine of theta is negative constant times sine of theta. Okay, the partial of y with respect to r, okay, well, r is a constant, r is a variable, that's a constant, and the derivative of a constant times r is just that constant. So that's going to give us sine of theta. And now the partial of y with respect to theta, okay, constant sine of theta, the derivative is constant times the cosine of theta. All right, so now let's take a determinant. That's going to equal to, all right, that's r cosine of theta times cosine of theta. That's r cosine squared of theta. Okay, minus, and now let's go backwards. That's going to be negative r sine of theta times another sine of theta is negative r sine squared of theta, which is double negative makes that a plus. So that's going to be r cosine squared of theta plus r sine squared of theta. Notice that I have a common factor, which I can go ahead and factor out. I can write that as r times the cosine squared of theta plus r sine squared of theta. Oop, not r. I've already factored out my r. R times cosine squared of theta plus sine squared of theta. But by the Pythagorean identity, that's always the number 1. Okay, so that's equal to r times 1, which is just r. So, given our previous theorem, what that means is if you're changing from xy into r theta, here, this Jacobian would be an extra r. So anytime you change from rectangular coordinates to polar coordinates, there'd be this extra mysterious r that would just show up, which of course we've seen going back several sections into this chapter. But this confirms what we already knew. Now, let's see one that we don't already know, because no one said that this transformation has to be one of the ones that we've seen. We can transform anything, and the way we're going to take advantage of that is to take regions that are complicated looking and convert them into simpler forms. So let's consider an example like that. So let's use our change of variables to compute the following double integral. Incidentally, this would also work for triple or quadruple integrals if need be, but again, for this section, we're just dealing with double integrals. Whatever mechanics we pick up here work the same in any higher dimensions. So let's see here. We're going to take the double integral over a region R of 60 times xy dA. Now here, they're going to give us an illustration for R. They've given us a picture. All right, so let's see here. Let's do 1, 2, and then that's about 1, 2. Okay, so we are going to have this sort of diamond shape where this is 0, 1, this is 1, 0. This will be 2, 1, and this will be 1, 2 up here. Okay, and our region R is all the stuff in between here. All right, now the way we're going to take advantage of this is by noting that our boundaries, even though we don't have a vertically or horizontally simple region the way we would like, we can think of them as having opposite sides that are of the same kind. Meaning here I have two linear equations that have a negative slope. Same thing over here. Now they're not the same, but they're related to each other. In fact, they're very closely related to each other. Note that this line right here is given by, well, let's see, it's got a slope of positive 1. And if I kept going back this way, it would cross through negative 1. Okay, so this is y equals x minus 1. Okay. This line right here has a slope of negative 1, and it crosses through 1. Okay, so this would be y equals to 1 minus x. This line right here is got a slope of 1, just like this one down here did. But instead of crossing through negative 1, it'll cross through positive 1. Okay, so y equals x plus 1. And over here, this one also has a slope of negative 1, just like this one. But if I follow this one up, it's going to cross the y-axis at, let's see, that's 1, 2. That one would cross up here at 3. So this would be y equals 3 minus x, just like that. Okay, so now let's consider what these equations look like and how we compare them. Consider the equation y equals 1 minus x, y equals 3 minus x. I'm just writing them next to each other. Consider the equation y equals x minus 1 and y equals x plus 1. Notice that pairwise, these are the same function of x and y with a different constant. Or in other words, this one right here, if you just add the x over here, that's x plus y is equal to 1. Over here, we can say, add the x over this way, that's x plus y is equal to 3. So here, what the substitution we want to make is, oh look, this x plus y appears several times. Let's call it u, or let's call it v, or we pick whichever one we like. I've already done the problem ahead of time to make sure it works out, so I picked v last time, so I'm going to go with that. So here I'm going to say, oh, all right, so then here, my substitution, I want v to equal to x plus y. Okay. Now over here, we have something similar. We can go ahead and subtract the y over and add the 1 over this way. So this will give me x minus y is equal to 1. And this one would give me x minus y is equal to negative 1. And again, I notice that x minus y is something that appears several times. So that's going to be a substitution that I want to make. I want to say, okay, instead of saying x minus y, let me just take x minus y and call it a single thing. In this case, I'll call it u. Okay. So now here, we have the ability to take x and y and turn it into u or turn it into v. But we're also going to need the ability in reverse. We're going to need to be able to say, okay, we need, how do we take uv and turn it into x? Right? Here we know how to take x and y, figure out what x is. To take x and y and figure out what u is. But we need to invert that as well. We need to know if you have u and v, what is x? Oh, well, that's going to be simple enough. We're just going to take these two equations and solve for one of the variables. So here, note that we're going to take these two. Let's say I have u is equal to x minus y, and I have v is equal to x plus y. Well, notice that if I add these two equations together, I get u plus v equals to double x, and then those cancel out. Oh, so that means that x must equal to 1/2 of u plus v. We're going to need both of these things here in a moment. Likewise, I need to figure out what y is, and that's simple enough as well. If I have this one right here, if I subtract these from each other, if I say this way, then that's going to give me u minus v is equal to, well, now these will cancel out, and negative y minus another y is negative 2y. So if I divide both sides by negative 2, that'll give me y is equal to negative 1/2 u minus v. And I could distribute the negative if I want to, but again, this will work out nicely. Mostly because I want these two to look similar, not because it's inherently necessary, but because it'll make my computation look easier at the end. It'll make things look a little neater. The closer these two look to each other and the closer these two look to each other, the nicer things will end up being. Okay, so now let's go ahead and go through using all of this information to transform our integral and to find our result. I want to write this in terms of u and v. Okay, so 60 is going to remain 60 because it's a constant. But x is no longer x. X is 1/2 u plus v. And y is no longer y. Y is now negative 1/2 u minus v. Like that. dA is now written as du dv. But don't forget, whenever we're changing, we need to find the Jacobian. So here, let's go ahead and find our Jacobian. We want to find del x del u, del x del v, del y del u, and del y del v. Okay, so we have all of these things. We have both of these equations, which means we can figure out our determinant. Here, if we take the partial of x, that's x, so that's x. The partial of x with respect to u, we're just going to get 1/2. If we take the partial of x with respect to v, we're also going to get 1/2. If we take the partial of y with respect to u, we're going to get negative 1/2. And if we take the partial with respect to v, we're going to get positive 1/2. All right, so that one's nice. So here, that's going to give us 1/2 times 1/2 is 1/4, minus 1/2 times negative 1/2, that's negative 1/4, and 1/4 minus a negative 1/4 is 1/2. Now remember, we want the absolute values of these, although in this case it does work out to be a positive number anyway. Okay, so there we go. That's our Jacobian. So up here, along with this du dv, we're also going to have this extra factor of 1/2. That is our Jacobian. And that is our Jacobian up here. Notice that it doesn't have to be variable. For polar coordinates, it's the variable r. For this transformation here that we've defined, it's just a constant 1/2. Okay? Now you need boundaries, but this is probably the best part of changing variables. Because you've changed variables to turn these variable equations into single variables, those single variables can now be bounded by constants. Or in other words, hey, look, I know x plus y goes as far as 1, and I know x plus y goes as far as 3, from 1 up to 3. Oh yeah, but x plus y is equal to v, which means v goes from 1 to 3. Okay, so that outer boundary is going to go from 1 to 3. Isn't that nice? We no longer have to worry about variables anymore. We don't have to worry about, oh, from left to right, from top to bottom, oh, these are variable equations. No. We've taken the variable part, condensed it down into a single variable, and that variable can now be defined as a constant. Same thing over here. X minus y is bound between 1 and minus 1. Oh yeah, but u is equal to x minus y, which means u is bounded between minus 1 and 1. Okay, so this inner boundary here is going to go from minus 1 to 1, just like that. We can now clean all of this up. Let's see here. Let's take all the constants out first. Half of 60 is 30. Half of 30 is 15. And then multiply that by negative a half. That's negative 15 halves. So that'll be negative 15 halves. The integral from 1 to 3 of the integral from minus 1 to 1 of, and all that's left now are my variables, u plus v times u minus v du dv. All right, I've taken all my constants out. Half of 60 was 30, half of 30 was 15, and 15 times negative a half is negative 15 halves. Here I can even multiply this out to make things a little nicer. I can take negative 15 halves, integral from 1 to 3, of the integral from minus 1 to 1 of, let's see here. That's going to be u squared plus uv minus uv. That's all gone. So that's just minus v squared du dv. And that's a nice, simple set of integrals with constant boundaries. So now it's just a straight up integration. Let's go ahead and do this part first. That would be, let's see here, negative 15 halves, the integral from 1 up to 3 of, if we're taking the integral with respect to u, that's now u to the third over 3, minus, that's a constant, so that's just the constant times the variable u, evaluated from u equals to minus 1 up to u equals to positive 1 dv. Let's see here, if we plug in 1, that's going to give us, well, let's see, negative 15 halves, the integral from 1 up to 3 of, let's see, if we plug in 1, that's going to be 1/3 minus v squared. So 1/3 minus v squared minus, if we plug in negative 1, that's going to be negative 1/3. And then that's minus a minus, so that'll be plus v squared. dv. And here, since these are opposites of each other, they're just going to double up. So this will give me negative 15 halves, the integral from 1 up to 3 of 1/3 plus 1/3, that's going to give me 2/3. Minus v squared minus another v squared is minus 2v squared dv. Okay. I can now just take that integral with respect to v. Well, that's just the regular old integral of, well, let's see, 2/3 integrated with respect to v is 2/3 v minus the integral of 2v squared with respect to v is 2v to the third over 3, evaluated from 1 up to 3, just like that. So that's going to give us, let's keep those separated here. That's going to give us negative 15 halves. If we plug in 3 right here, that's just going to give us 2 since those would cancel out. So it's going to give me 2 minus. If I plug in 3 right here, that's 27 divided by 3 is 9. 9 times 2 is 18. And then minus, and then right here I'm going to go ahead and plug in the number 1. So that'll give me 2/3 minus, and then also gives me 2/3, just like that. So this will give me negative 15 halves times 2 minus 18. That's going to be negative 16 minus 0. And here, that's going to give me, oh, let's see, double negative makes that a positive. 16 divided by 2 is 8. And 8 times 15, that'll give me 120. And that's our result. So if we take the integral of 60xy over this region, we can change our boundaries. Don't forget to take your Jacobian as well. We change x into this, we change y into this. Okay, so we change x into this and y into this. When we transform this into this, don't forget your Jacobian. And now, thanks to your transformation, these integrals now have nice constant boundaries as opposed to variable equations that we had before. And finally, go through your integration. At this point, it's a nice double integral with constant boundaries. That's what makes it nice. And you get your answer. All right, let's take a look at one more example here. In your assignments, some of the problems ask you to come up with your own substitutions and your own boundaries, just like we did here. And that's the way you would do it. You would write out your equations, and then you would look for some commonality between pairs of boundaries. You would say this one and this one are paired because they both look the same. This one and this one are paired because they also look the same. X minus y versus x plus y, things like that. And some of the more complicated ones, they have a little bit of mercy on you and say, okay, this one might not be super obvious. So in some of them, they actually tell you what your substitutions are supposed to be. So that's what this one looks like. We're told to find the double integral over the region R of y sine of xy dA, where our region is given by this funny looking object. We're given a lower bound, y equals to 1. So y equals to 1. We're given an upper bound of y equals to 4. You say, well, that's not so funny looking. It's a rectangle so far. Well, sure. But the sides are a little bit less cooperative at first. We have this, and we have this, like that. So here, this equation is given by, oh, what did they give us? They told us x is equal to, what did they give us? Oh, they gave us xy equals to 1 and xy equals to 4. And our region that we care about is the stuff in between here. All right. So all of that was given to us. Before, we had to find our own equations and we had to find our own substitutions. But here they've told us, okay, go ahead and do that and use the substitutions. Let u be given by u over, let x be given by u over v. And let's go ahead and have y given by v. If you went through the whole procedure that we did for the previous one, you would eventually get those substitutions. Just like over here, we got, here's what our u is, here's what our v is. We eventually got that, but here they were nice enough to just say, oh, by the way, here they are. All right? There's still some work to do, but these were a little less obvious to set up than the previous ones that were linear. So here they went ahead and gave us some substitutions. Okay, well here we've been given how to find x given u and v. We've been given how to find y given u and v, but we need to go the other way around. Okay, well this one makes it easy, because if y is equal to v, that means v is equal to y. And if v is equal to y, well, then that means that if I want to find out what u is, I can say, well, let me multiply this over to the other side, v times x, and I can replace the v with a y, so that becomes y times x. So here u is equal to x times y. Right? That one's simple enough. If v is equal to y, then y is equal to v. And if I just plug this in over here, that becomes a y. U over y is equal to x. So multiply that over to the other side, and now u is equal to x times y. So those are our substitutions. Okay, don't forget we need to compute our Jacobian. That's going to be the partial of x with respect to u, the partial of x with respect to v, the partial of y with respect to u, and the partial of y with respect to v. Take the magnitude of that and absolute values if need be. All right, so here we're going to take this as the partial of x with respect to u. Okay, well, there's x. And with respect to u, well, that's u over a constant, which if I take the derivative, it's just going to be 1 over the constant. The derivative of x with respect to v, that's going to be the derivative of this with respect to v. Oh, I'm sorry, I'm looking at, oh no, I'm taking these one at a time, aren't I? So here the derivative of x with respect to v, that's going to be a constant over v, which if I take the derivative is negative 1 over double, oh no, not over double, I'm thinking it was square root. So that's negative 1 over v squared. All right, that's just a constant. So ignore the constant for a second. The derivative of 1 over v is negative 1 over v squared, but then, well, that is a constant, so that should be brought in. Just like that. The partial of y with respect to u, well, there is no u. Okay, so then this is just a constant. Oh, the derivative of a constant must be 0. And here the derivative of y with respect to v, well, the derivative of this is just 1. Okay, so now my determinant is going to be 1 over v times 1, which is still 1 over v, minus anything times 0 is 0. So that's 1 over v. All right, so coming up over here, that's going to be my Jacobian. So let's start with our transformations here. This is going to be the double integral. We're going to write this as an iterated integral. All right, let's see. Y. Well, we know y is just being replaced by v. That's what y equals v. Sine of x times y. Well, again, we know x is u over v. And again, we know y is v. All right, so y becomes v, x becomes u over v, and y becomes v. And dA is going to become du dv along with our Jacobian. So it's going to be times 1 over v. I would say absolute value, but all of our numbers are now positive. We don't worry about that anymore. All right, 1 over v. Here, v is going to be a set of positive numbers. Notice all of our boundaries are positive. Everything's in the first quadrant. And that's going to be times 1 over v du dv. And now let's talk about our boundaries. Because after all, here we have u. It's going to go from, well, let's see. U is equal to xy. Oh, but xy has the smallest value of 1, and xy has the largest value of 4, which means u must have the values from 1 to 4. So here this one must be u is equal to 1, and u is equal to 4. So those must be our boundaries. U goes from 1 up to 4. Here we have these, y is equal to 1 and y is equal to 4. But again, y is the same thing as v. So here that means v goes from 1 up to 4. Okay, so that's going to go from 1 up to 4. And there we go, there's our setup. Notice that a bunch of things simplify here. I can now take these and divide. V over v. Same thing over here. This v over this v. And now we're left with a very, very simple integral, namely the integral from 1 to 4. Let me go back to blue. The integral from 1 to 4 of the integral from 1 to 4 of sine of u du dv. That's all that's left. This is the main advantage of using these kinds of substitutions. This is not simple. All right? This is not at all simple in the xy plane. Everything's variable. But by changing your variables, now all of your regions are simple, both vertically and horizontally. And in other words, every boundary is constant. So now things are nice. If I take the integral with respect to u of the sine of u, I get negative the cosine of u. And I can substitute in these values. These aren't going to be nice values, but oh well. Right? I'm going to get the integral from 1 to 4 of negative the cosine of 4 minus negative the cosine of 1 dv. That's going to give me the integral from 1 to 4. Double negative makes that a positive, so let me put that in the front. That's going to be the cosine of 1, and then here that's going to be minus the cosine of 4 dv. But now notice, even though these are unusual constants, we don't usually see cosine of 1 radian, cosine of 4 radians. Usually we see multiples of pi. But whatever, those are numbers. And so now if I'm taking the integral with respect to v of a number, well, that's going to give you that number times v. So that's the integral from 1 to 4 of that constant, cosine of 1 minus cosine of 4. Oop, I've already taken the integral. Times v, evaluated from wherever v is equal to 1 up to wherever v is equal to 4. And so that's going to be, well, 4 of this minus 1 of this, which will give me 3 of this. So this gives me 3 times the cosine of 1 minus the cosine of 4, or if you prefer, you can distribute that out. 3 cosine of 1 minus 3 cosine of 4. Which I'll say would probably be not nice to do in the XY coordinate system. When you get an answer that looks like that, that's probably not something that's friendly in the XY plane. But with our change of variables, we now have our result. And that's it. So that brings us to the end of our section. For an assignment, go ahead and try the following. Section 14.8, 1 through 7 odd. That just tells you find the Jacobian given some transformations. It doesn't go through an entire problem. It just has you do this part, just so you get familiar with the organization of a Jacobian. Then try 15 through 23 odd. 15 through 23 odd. Here, most of these are going to tell you what your transformation is. They'll tell you that. But the very last two, 21 and 23, will not. It'll be up to you to find out what your boundaries are, what your transformation is. However, the last two are also very simple regions. One's a parallelogram and one's a triangle, I believe, or something like that. Oh, sorry. One's a parallelogram, one's a square. So here either you'll be given the boundaries or the last two you'll be told to find your own, but the shape will be very, very simple so that you can do that. And finally, try number 39. In this section, we've only seen the Jacobian of two variables, a 2 by 2. Number 39 will show you what a Jacobian for 3 variables will look like, a 3 by 3 matrix whose determinant you'll take. It will look exactly the same. It'll be del x, del u, del x, del v, del x, del w, del y, del u, del y, del v, del y, del w, del z, del u, del z, del v, del z, del w. So it'll be a 3 by 3 matrix, and you'll take its determinant to find a Jacobian. Number 39 has you confirm something that I've pretty much just been hand-waving the entire time. It'll have you confirm the Jacobian for spherical coordinates. It'll have you show that when you convert to spherical coordinates, you should get rho squared sine of phi, the way we have been taking for granted for this section. So that is it. If anybody has any questions, please reach out to me. Make sure you write down what your questions are. Make sure you let me know. And I hope you all have a nice day.